Last material in chapter 13 is called the chi-squared homogeneity test. So this is section 13.5. And this is going to be a test that's going to be used. So you're going to have different populations, and this test is going to be used to determine whether or not these populations are the same or not, whether they have the same makeup or not. So whether they have the same makeup or not is whether they're called homogeneous or not. So if they all have the same makeup, they're called homogeneous. Okay, so the same type. If at least two of them are different, if at least two have different makeups, then they're called not homogeneous. Okay. So this chi-squared homogeneity test is going to be very similar to the chi-squared dependence test. In fact, all the formulas are identical. The expected value is the row total times the column total divided by the sample size. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. The chi-squared test statistic is exactly the same. You're going to store your data as a matrix. And the way that the hypothesis test is going to run is that the null hypothesis is always that the populations are homogeneous. The alternative hypothesis is that they're not homogeneous, meaning at least two are different. Interestingly, when R is 2, the chi-squared homogeneity test is exactly the proportion test that we talked about in chapter 12, which is why the proportion test had that chi-squared term in there, is because it's really a chi-squared test. Okay, you don't really even need to know that to do the prop test function and the chi-squared test function, but those are basically the same thing. So what I want to do is I want to look at the following example. And so this is data that was obtained regarding different types of hospitals in the US, categorizing them according to basically 4 categories: general, psychiatric, chronic, or other. And then the data also made note of another variable in which it was how it was organized. Was it government run? Was it proprietary, meaning that they were going for profits? Was it not for profit? And then here's what they found. So they list the totals here. So of the general hospitals, 1,697 of them were government run, 660 were proprietary, and then 3,046 were not for profit. Okay, for a total of 5,403 hospitals that were general hospitals, and so on for the rest of the data. Okay, and so altogether there were 6,580 hospitals. And what we want to know is at the 5% significance level, do the data provide sufficient evidence to conclude that there's a difference in hospital types for government, proprietary, and NFP hospitals? NFP meaning not for profit. I probably should be consistent with myself. Sometimes these are called NFP, sometimes these are called NP, but just not for profit hospitals. Okay, so at the 5% significance level, is there sufficient evidence to conclude that a difference exists? Okay, that they're not homogeneous. So the way that we're going to do this, since we've already done this by hand, kind of the painful way, the way that we're going to do this is I'm going to store everything in R. Okay, and so we'll store in R all of our data. So let's jump over to R. So we'll pull that up. We'll just run everything in R. And in R, what we're going to have is for the general hospitals, we'll have 1697, 660, 3046. For the psychiatric hospitals, which we'll call PSY, we'll have 266 government run, 354 proprietary, and 113 not for profit. For the chronic, which I'll call CHR, there were 21 government run, 1 proprietary, 4 not for profit. And for the others, there were 62 government run, 148 proprietary, and 204 not for profit. Okay. Again, one thing I like to do is if I just look at the sum of these values, the general, the psychiatric, the chronic, and the others, there should be 6580 if I made no mistakes, and there we go. So again, that's just kind of a way to, it's not going to catch all your mistakes, but it's one more thing that you can do just to catch some mistakes if you make them. I'm going to let M be our matrix. And what we're going to do for our matrix is we're going to store Let's see, we're going to have our data will be the general hospitals, the psychiatric hospitals, the chronic hospitals, and the others. We're going to have, let's see, 4 rows. So 4 rows and 3 columns in this case. And I'm going to sort by row. I always just automatically sort by row. That's the way that I think about matrices. So I usually put by row equals true, but if you instead of storing the rows, if you wanted to store the columns, then you wouldn't have to put anything in this matrix part. Okay, so here's our matrix M. Okay, so this is all the values that we had before. And then what we're going to do is at the 5% significance level, we're going to say, is there enough data to say that there's a difference in hospital types for government, proprietary, and not-for-profit hospitals? So we're going to run a chi-squared test over our data M. We're going to not have a correction term. Okay, so again, just like in chapter 12, we always have to add in the correct equals false code. And what we get is a huge chi-squared value and a tiny p-value. Okay, and so here we can say with lots of evidence, with lots of certainty, that there is a difference. Okay, so here our p-value is 0 to 16 decimal places. That's what this e to the negative 16 means. It's 2.2 times 10 to the negative 16. And again, like we said before, we had 6 degrees of freedom. Our chi-squared term was huge. Okay, so 848. So here there is enough data to reject the null hypothesis. So in other words, yes, there does exist a difference in hospital types.